Please, Kevin,
Okay.
welcome.
Thanks, Fedor, and thanks for having me, everyone. So I'll be talking about some new, newish kind of algebraic methods in parameterized and exact algorithms. Okay, so I'll start by motivating our approach, and the motivating problem for this whole talk will be that of counting or detecting simple cycles, so cycles in a graph that don't repeat any vertices. So this will be the running problem throughout the talk, but we'll see very quickly that more generally the problem we'll be interested in is that of detecting or approximately counting multilinear monomials in some polynomial that's given to you either as an oracle that you could just evaluate or as a circuit. And our first approach to this general polynomial problem will be by exploiting the certain upper bounds on the so-called Waring rank of certain polynomials. And this is based on work of mine from the past Fox. And with this approach, we'll give some algorithms for exactly and approximately counting simple cycles in a graph. And I should also say there's lots of history behind this problem and other problems which our approach could be applied to. I'm not going to talk too much about the history, except I'll say that the 4.0 for approximately counting simple cycles, there are faster algorithms than this base 4.075 to the D. And okay, so I'll mention some details about like how much space these things use. They use polynomial space. I'll mention that briefly, but I'll mainly just be like showcasing this approach and focusing not so much on the particular results for this problem. And this approach will lead to another approach, which is based on joint work of mine with Cornelius Brand. And this is based on upper bounds of something called the dimension of the space of partial derivatives of certain polynomials. And this approach is kind of a relaxation of the previous one. And using it, we'll give a deterministic algorithm for detecting simple cycles of length D in a graph. And has this curious runtime, which appears in several papers. And I'm not sure why that is, but I'll talk about that at the end a little bit. Yeah. And so then we'll just give some concluding remarks. But if you get anything out of the talk, is that there are some very self-contained elementary algebraic questions that lead to some like very general and simple approaches in parameterized algorithms. So it's kind of a very simple like conceptual framework. And furthermore, we don't know a reason why you couldn't like significantly break the state of the art in terms of upper bounds. So we don't know why you couldn't obtain, for example, a 2 to the D poly n 1 over epsilon time algorithm for approximately counting simple cycles using our approach, even deterministically. And we'll see some very explicit algebraic problems whose answer is closely related to this question. So let's talk about this problem now. So we start with the observation that a lot of the times you can encode solutions to hard combinatorial problems in the coefficients of some generating polynomial that's easy to compute. Okay, so you have this easy to compute polynomial, like it's computed by a small circuit, but its coefficients are some, encode some hard information. And the goal of the whole talk will be to extract this information by computing certain linear combinations of these coefficients. So this is our approach for the whole talk. So as our running example, let's say we have a graph G on n vertices, and we'd like to count the number of simple cycles in G of length D. Usually people use the letter K And also, I think the k path, it's more common to use the example of counting paths, simple paths in a graph. But I use D here to emphasize that it has something to do with the degree of a polynomial. And I like the generating polynomial more for cycles than paths. So you're given this graph, and you start by defining this matrix I call A sub G, whose ijth entry is going to be the variable x sub I when there is an edge from the ith vertex to the jth vertex in the graph. And we set this entry to be 0 otherwise. Okay, so you have some matrix. Each entry is either a variable or 0. It's an n by n matrix. Now, there's this kind of folklore result that's not too hard to prove. I'm not going to prove it though, which is that when you take the trace of the dth power of this sort of symbolic matrix, what you get is a sum over all the closed walks in the graph of length d of the product of the variables associated to the vertices in the graph. Okay, so recall that we have this way in which we associate the variable x sub I to the edge going from the ith vertex to the jth vertex. Okay, and the key observation here is that when you have a simple cycle in the graph, when you have a simple cycle in the graph, the monomial you'll get here on the right-hand side is going to be multilinear, or square-free, you might call it, just meaning that the highest power that a variable will appear raised to is 1. You have no variables that are squared appearing in this monomial. And so in particular, when you take the sum of the coefficients of all of these multilinear monomials in this generating polynomial, what you get is the number of simple cycles of length d in the graph. Okay, and it's kind of ordered, so you actually count each simple cycle d times. So we're in this situation where we have this generating polynomial. It's just the trace of the dth power of this matrix. It's easy to compute. I mean, it's just multiply matrices and take the trace. And we want to compute the sum of the coefficients of its multilinear monomials. Okay? So just as a quick example, if you have this graph G, just a directed cycle, with a self loop, then you have this sort of symbolic adjacency matrix. You got AG, and when you take the trace of its cube, what you get is, what I said, it's the sum over all the closed walks of length 3 in the graph. So you have this closed walk from x1 to x1 to x1 of length 3, then you have one from 1 to 2 to 3, and from 2 to 3 to 1 to 2, and so on. And so what you get is x1 cubed plus 3 times this multilinear monomial, x1, x2, x3. And so here we want to compute and return this value of 3. Okay, so here's a little bit of formalism, which will help us. So we'll let SD to the n be the vector space of homogeneous degree d polynomials in n variables with real coefficients. So homogeneous, recall, just means that so every polynomial is some linear combination of monomials, each of which has some total degree, the sum of the exponents that make it up. And we say it's homogeneous if all of these monomials have the same total degree. Now we'll define this map which turns out to be an inner product. It takes two things in this vector space. So it takes two polynomials, degree d, and then variables. And what it does is you replace the variable x sub I in your polynomial f with the differential operator partial xi. And now what you have is it's some differential operator, right? You just formally replaced the variables with partial variables. And in particular, you can use it to differentiate something, in particular g. So you replace the variables in f by partial differential operators, and you apply this whole thing to g. Okay, it's a very simple thing, actually. So, for example, if you want to compute this inner product between 2x1 squared minus x2x3 and x2x3, so first what you do is you just replace the variables, replace x1 with partial x1, and replace x2 in the first operand with partial x2, and so on. And you get this thing, which is just some differential operator. And then you just apply it to x2, x3. Okay, so this is just like ordinary differentiation now. So you expand everything out. Here you get 0, and here you get -1. So what you get is -1. And it's more explicitly, if f is just this polynomial with coefficients a sub I1 through In, and b is this polynomial with coefficients b I1 through In, then this inner product is basically just the dot product of these coefficient vectors, but you will scale by some factorials that arise when you differentiate. So it's some scaled dot product of the coefficients. And that's it. Okay, so just rephrasing our previous observation of simple cycles in graph. So if we take the inner product between the elementary symmetric polynomial of degree d and n variables, which I call END, and this is just defined as the sum over all square-free or multilinear monomials of degree d and n variables. So this is an important polynomial for us. It'll come up repeatedly. So when we take the inner product between this thing and this generating polynomial, this trace thing, what we get is just the sum of the coefficients of this multilinear monomials in the generating polynomial. Okay, and that's just because if you differentiate this if you differentiate a polynomial by a homogeneous degree d polynomial by a multilinear monomial of degree d, then what you get is just the coefficient of that monomial in your generating polynomial, okay? And when we take this elementary symmetric polynomial, we sum over all multilinear monomials. So the inner product gives us the sum of all the coefficients of these multilinear monomials. Okay, so this is mainly just notation for now. We'll see how it becomes useful in a bit. So our first goal will be to compute this inner product with a polynomial g and this elementary symmetric polynomial. We would like to compute it quickly as possible, right? And this will give us the sum of the coefficients of the multilinear monomials. That's all this. That's all this quantity is. Just another name for that quantity. Okay. So our first approach will be through looking at upper bounds on Waring rank. Okay. So what is Waring rank? Okay. So we're given some polynomial of degree d, and we say that it's called f, and we say that its Waring rank is the smallest number r, so that we can express f as some linear combination of dth powers of linear forms. And that's just another word for homogeneous linear polynomials. So we'd like to decompose a polynomial f in this way. as a simple example, if you take the monomial x1, x2, x3, then you can check by hand or with a computer that it can be expressed as the following linear combination of 4 cubes of linear forms, okay? So you have these linear forms with these like alternating +1, -1 signs. And this shows that the wearing rank of this monomial is at most 4. Okay, so hopefully that's clear what wearing rank is. And so wearing rank has been studied for like a very long time, at least since the 1800s. There's a lot of history behind it, and it continues to be studied in like algebraic geometry today. We won't really use any complicated facts about it though. The main thing we'll use is the following very old observation, at least 150 years old. And it says that if the wearing rank of some polynomial f is at most r, then for any other polynomial g, any other homogeneous degree d polynomial g, the inner product between f and g is determined by the value of g at some set of r points. Okay, so there's some r points that will tell you for any other polynomial g what the inner product between f, your fixed polynomial f, and g is. Okay, so I'll give the proof of this, which should be a little bit illuminating as to what this actually means. So the first claim is that when you take this inner product between a dth power of a linear form, say with coefficients a1 through an, and the polynomial g, that what you get is just some scalar, d factorial, times g evaluated at the point a1 through an. Okay, and this follows just by expanding everything out and comparing coefficients. Okay, and this holds for any polynomial g. Okay. And now, say we want to compute this inner product. So what you can do is, you have an upper bound on the wearing rank of f. So you plug in the upper bound for f. And since this inner product is bilinear, you can now split this inner product into a sum of smaller inner products of this form. Okay, and then by applying this identity here, you get that this inner product is just d factorial times this linear combination of evaluations of your polynomial g. Okay, so essentially the points in the wearing decomposition for f are the points you should evaluate g at to compute this inner product. Okay, so back to the example of the simple cycles. So we wanted to compute this inner product between the elementary symmetric polynomial and this trace dth power polynomial. Now, by the previous observation, this leads us to ask, what is the wearing rank of this elementary symmetric polynomial? Because an upper bound on this, the rank of this, gives an upper bound on the number of points that we can evaluate this trace polynomial at to compute the inner product. And so there's a general upper bound on wearing rank. So the wearing rank of any polynomial is finite. It's some binomial coefficient. So it's the binomial coefficient n plus d minus 1 choose d. And in particular, this holds for the elementary symmetric polynomial of degree d and in variables. But actually, it turns out, it was shown by Lee, that the wearing rank of this polynomial is like the square root of that, kind of. So the wearing rank of this polynomial is actually equal to the sum of the first d over 2 nth binomial coefficients. Okay, and for very large n compared to d, this is like n to the d over 2. Okay, And we'll be interested in this setting where n is much bigger than d is, because parameterized algorithms. So what this tells us is that if you have a graph G on n vertices, the number of length d simple cycles in the graph is determined by the value of this trace polynomial at n to the d over 2 points. Okay. And actually, the algorithm is for computing the sum of these coefficients. Right, the algorithm for computing the number of simple cycles is like very simple. It like fits on one line. It's just the following linear combination of evaluations of this generating polynomial. Okay, so it gives you some very simple algorithm for counting simple cycles in a graph, and it runs in time n to the d over 2 times poly n, and it inherently uses polynomial space. You just compute it iteratively. And so at the time, this was, I believe, the first polynomial space n to the d over 2 time algorithm for this problem. And this also applies to other problems like counting simple paths, and yeah. So more generally, what we have is that given oracle access to a polynomial G, you can compute the sum of the coefficients of its multilinear monomials using n to the d over 2 evaluations. Okay, and also let me say something else about the runtime of this problem. So I believe the fastest algorithm has runtime like something like n to the 0.17. Someone in the audience might maybe a co-author on this. I'm just doing this off, I'm just recalling this off the top of my head. So this n to the 1.7d. So n to the d over 2 is not the fastest in general. But the point was at the time that it only used polynomial space. Okay. So you get this simple algorithm. And now you might ask yourself, can you do faster? At least say in this model where all you can do is evaluate the polynomial G. And so I showed in my paper that you can't. So I showed that if you have some fixed polynomial f and you have oracle access to G, then you actually need the wearing rank of f many queries to G to be able to compute this inner product. So in particular, when f is the elementary symmetric polynomial, you need n to the d over 2 queries to compute this sum of the coefficients of its multilinear monomials. Okay, so you can't improve this in this black box kind of setting, but you could still try to do better. So some workarounds, natural workarounds, would be just to approximately compute this quantity, or maybe think about the white box setting. And something else is that this theorem here really uses the fact that G, you don't know anything about G. So it could be any polynomial. Like it could be, very hard to compute polynomial. But for all our applications, the polynomial G will have special properties. It'll at least be easy to evaluate. So maybe you could exploit that to get around this. Okay, now what we'll focus on in this talk, the next part of this talk, is the problem of approximately computing the sum of the coefficients of these square-free monomials in G. And we'll continue with the wearing rank approach. So the first order idea would be, actually, let me just check chat for a second. Oh, actually, could I ask if there are any questions, Fedor? Because
Doesn't look so.
Okay. Let me share my screen again. Okay. So here's an idea for approximately computing this quantity. What if we had some polynomial f that had low wearing rank, much lower than that of the elementary symmetric polynomial? So like much less than n to the d over 2. And we want it to have the property that for any other polynomial g that you take, that's homogeneous of degree d, when you take the inner product between f and g, the number you get is bounded between 1 minus epsilon times what you would get if you took the inner product between the elementary symmetric polynomial and g, and 1 plus epsilon times that quantity. Okay, so this, this would be great because it would give us some small number of set of points that we could evaluate g at to approximately compute this inner product. Now, for kind of silly reasons, this doesn't work exactly, and that's just because without the restriction that g has to have non-negative coefficients, at least on its multilinear monomials, you have to have the only such f is when f is this elementary symmetric polynomial itself, which is, we already know what happens then. So we actually want that this property should hold for all g that, say, have non-negative coefficients. Okay. And an equivalent condition, which is the one I like to think about, is that, so you start with the elementary symmetric polynomial, okay? And then you're allowed to wiggle the coefficients of the non-zero monomials in this elementary symmetric polynomial by epsilon, okay? So you have some set of polynomials that you can obtain by wiggling these coefficients a little bit. And the question is, how low is the rank? How low can you make the rank of this polynomial by wiggling the coefficients by epsilon? By wiggling the coefficients of the non-zero monomials, the monomials that actually appear. Okay, and we'll call this quantity a epsilon of n comma d. And so for algorithmic reasons, we'd like to upper bound this quantity. Okay. And just another way of thinking about the relevance of this quantity, or what it says, if you just knew an upper bound, it would tell you an upper bound on the size of the circuit that approximately computes the number of simple cycles of length d in a graph. Okay, and this requires a bit of explanation, but it follows pretty quickly from some previous observations we've seen. And I mention this because, you might have an upper bound on this a epsilon of n comma d, and it might not be explicit. You might not know, you might not know the linear forms that give you the upper bound, and you might not know what the polynomial f is exactly. But nevertheless, it gives you some kind of non-trivial circuit upper bound. So essentially, even a non-explicit upper bound on this quantity is interesting in my opinion. Although the upper bound that I'll give is sort of like semi-explicit, like explicit enough that it gives a uniform family of randomized algorithms. But I'll just present the result as an upper bound on a epsilon of n comma d. Okay. So what I showed was that a epsilon of n comma d it's at least 2 to the d minus 1, and it's at most 4.075 to the d times log n over epsilon squared. Okay. So start with the lower bound. So in particular, see this lower bound here. You're not going to beat base of the exponent 2 for like approximately counting simple cycles of length d using the approach as I've like directly outlined it here. So that's just something to note about what this lower bound tells us. So to prove the lower bound, we start with the observation that if you have a polynomial and you start setting some of its variables to 0, you do not increase the Waring rank. Okay, and that's a trivial statement. So this tells us that this a epsilon of n comma d can only get smaller as we decrease n. Okay, and in particular, a epsilon of d comma d is a lower bound on a epsilon n comma d. Okay, but what is a epsilon of d comma d? Well, by definition, what we were doing is we were starting with this monomial. We're starting with the elementary symmetric polynomial of degree d and d variables, which is just this monomial here. And then you're allowed to like wiggle the coefficient in front of it by epsilon. Okay, but it's easy to see that Waring rank does not change by scaling. And so, you know, a epsilon of d comma d just is the Waring rank of this monomial. But now it was shown by Reinstad and Schreier that the Waring rank of this monomial actually is equal to 2 to the d minus 1. Okay, so that's the lower bound. The upper bound is some kind of combinatorial hashing argument. It's very reminiscent of previous algorithms and previous parameterized algorithms for approximate counting. So we start by setting this parameter n0 to equal 1.55 times d. Okay, this is carefully chosen to minimize some function at the end. And we suppose that we have this family of functions, call it script f. And each function in this family goes from 1 through n to 1 through n0. And so suppose we have this family f with the following property. So we would like for there to exist a number t, so that for every subset of 1 through n of size d, the number of functions in script f that are 1-to-1 on the set S is between 1 minus epsilon times t and 1 plus epsilon times t. Okay, so this object was first defined, I think, by Alone and Gutner, and they called it an epsilon comma d balanced family of hash functions. Okay, so suppose we have such an f. Now, we want to define some polynomial with Waring rank at most 4.075 to the d log n over epsilon squared that has the desired property and that it's sort of close to the elementary symmetric polynomial. Okay, so how we'll do this is by defining the linear forms, call them L sub pi comma j, for every function pi in script f and every number j between 1 and n0. And we'll define L of pi comma j as the sum of all the variables x of I, where I is mapped from, where pi maps I to j. Okay, so you define some linear forms, and now what you do is you consider this polynomial obtained by summing over all functions pi in script f of this elementary symmetric polynomial evaluated at these linear forms L pi 1 through L pi n 0. Okay, and we're going to claim that this polynomial basically has, it witnesses the upper bound we like on A epsilon of n comma d. So why is this? Well, first, note that by definition, for any pi, L pi comma 1 through L pi comma n 0, this set of linear forms, no two of them share a variable, okay? So they're linear forms in disjoint sets of variables. And also, the elementary symmetric polynomial is a multilinear polynomial. And it follows from this that if you plug in some linear forms and disjoint sets of variables into a multilinear polynomial, what you get is going to be itself multilinear. And so in particular, when you sum over a bunch of these things, it's still multilinear. And so f is going to be multilinear. Okay, so f does not have any unwanted monomials appearing. It doesn't have any multilinears with squares appearing, which is what we want. It's the first thing we want. And the next thing we want is to show that the coefficients of all these square-free monomials of degree d appearing in f have coefficient between 1 minus epsilon and 1 plus epsilon. So consider, for example, the coefficient of x1 through xd. So what will this coefficient be? Well, we get a contribution to this coefficient exactly when the variables x1 through xd are split amongst these linear forms. That is, when no two of them appear in the same linear form. Okay? And how many times will this happen? Well, by definition of these linear forms, this happens exactly when the function pi was 1-to-1 on the set 1 through d. Okay, but by definition, so by definition of script f, this is just between t times 1 minus epsilon and t times 1 plus t times 1 minus epsilon and t times 1 plus epsilon. Okay, so if we divide f by t, you get a polynomial that has this desired property. So it witnesses an upper bound on A epsilon of n comma d. And the last thing to do is do an upper bound on its Waring rank. And we do so by first observing that Waring rank is subadditive. Okay, so this is just another basic property of Waring rank. It's not too hard to see. And so this tells us that the Waring rank of f is at most, the number of summands appearing here times the rank of each one. So the Waring rank is at most the size of script f times the Waring rank of this elementary symmetric polynomial. Okay, and the theorem follows by some calculations. So first you have to upper bound the size of a minimal script f, which can be done by a standard randomized argument. I think it also appears in the paper Alone and Gutner. And then you just use the bound on this elementary symmetric polynomial, E n0d, which is just E 1.55 comma d, recalling the definition of n0. So using the bound of Lie on the rank of that, you get the desired upper bound on A epsilon of n comma d. Okay, so this is some upper bound on this, and I'm not going to state it explicitly in the talk, but it gives a randomized algorithm for approximately computing the sum of the coefficients of square-free monomials. Which, by the way, could be made which could be de-randomized if you know an explicit construction of this kind of balanced script f of like nearly minimal size, which may be known, I'm not sure. But I showed this upper bound on A epsilon of n comma d. It gives some algorithms for approximately counting things like simple cycles, but unfortunately, I don't know how to improve it anymore. Although I do not think that it is optimal. I think it could be improved, but I just don't know how to right now. So here's a relaxation. Maybe we could find an improved answer to this. So let's, instead of looking at looking for a polynomial f that was obtained by wiggling the coefficients of the elementary symmetric, the non-zero coefficients of the elementary symmetric polynomial by epsilon, let's look for another polynomial, that f with a much weaker property, which is as follows. What we want the property we want f to have is that when you take the inner product between the elementary symmetric polynomial and any polynomial g with non-negative coefficients, the thing you get should be non-zero exactly when the inner product between this thing we're looking for, f and g, is non-zero. Okay, so more concretely, this is just saying that f is obtained in the following way. So you start with the elementary symmetric polynomial, okay? In which case this coefficient would just be 1. And then you're allowed to just change the coefficients of those square-free monomials to anything that's greater than 0. Okay, it doesn't have to be close to 1, it could be anything greater than 0. And we'll define a plus of n comma d as the smallest Waring rank of a polynomial f that you obtained in this way. And this upper bounds on this kind of are analogs of deterministic decision algorithms for like detecting simple cycles. If you actually knew an explicit upper bound on a plus n comma d, it would just be, I mean, you could use it as an algorithm for deterministically detecting simple cycles or paths and so on. So, of course, a plus nd you're asking for a much weaker condition on f. So it's at most a epsilon of n comma d for any epsilon. So in particular, a plus nd is at most this bound 4.075 to the d times log n. Here we just took epsilon to be 0.1, for example. Okay, but I know another bound for a plus n comma d. And it's explicit. I mean, the polynomial that witnesses it is explicit. So we define hn comma d as the sum over square-free monomials of degree d and n variables, where the coefficient of any monomial appearing in H is going to be the product of the squared differences between any two different indices, any two different subscripts on the variables. Okay? So clearly this is an upper bound on a plus n comma d. The Waring rank of this is an upper bound on a plus n comma d. So for example, h of 3 comma 2 is some polynomial in 3 variables of degree 2. It's the sum over all those square-free monomials where the coefficient is given by the square difference of the two subscripts appearing. So 1 and 3 minus 1 squared is 4. Okay. So the upper bound I know on A plus at n comma d is, or on the Waring rank of this polynomial h, is 6.75 to the d. Okay. It's a simple proof. I'll just give you the idea of it though. The idea is that h of n comma d can actually be expressed as a polynomial in only 2d minus 1 variables. That is, there is some polynomial f in only 2d minus 1 variables of degree d. And you can obtain this h by plugging in some linear forms into the inputs of f. But f is polynomial. Okay, so this tells us that an upper bound on the rank of f is an upper bound on the rank of h. But by this general upper bound on Waring rank, in terms of the degree and the number of variables, you conclude the desired Waring rank upper bound. Okay. So here's a question: is the Waring rank of this polynomial h, what is it? I mean, is it better than the 6.75 to the d thing? Is it like big O of 2 to the d? Because if it was like big O of 2 to the d, and you knew an explicit upper bound, then you would have a deterministic 2 to the d times poly-n time algorithm for detecting simple cycles in the graph, which is a major open problem in parameterized algorithms. So I know an upper bound, but on the rank of this particular polynomial, could you prove a lower bound? It's better than 2 to the d to rule out this approach. So there's basically one known method for proving Waring rank lower bounds, and it's the following. So if you're given some polynomial f, we're going to associate some vector space to f. And the way we define this vector space is as follows. You take f, and you start taking all the partial derivatives of f that you possibly can. And you look at the vector space that they span. Okay, so you have a bunch of this big set of polynomials, you look at the space they span. And we're going to be interested in the dimension of this vector space. Okay, and I'll call this vector space diff of f. So for example, if f is equal to x1 times x2, then diff of x1, x2 is going to contain the polynomial x1, x2 itself, as well as what you get by differentiating by x1, which is x2, and what you get by differentiating by x2, and what you get by differentiating by x1 and x2. Okay, and it's not too hard to see that this set of polynomials, 1, x1, x2, and x2, x3, actually span the space diff of f. So diff of x1, x2 is the span of these monomials. And the reason why we care about this vector space is the following classical fact relating it to Waring rank, which says that for any polynomial f and for any number I between 0 and d, the Waring rank of f is at least the dimension of the degree I part of the vector space f. Okay, and when I say the degree I part, I mean the space spanned by the degree I elements in diff f. So for example, if I is equal to 1 for here, well, what are the degree 1 things? They are x1 and x2, and they span a vector space of dimension 2. Okay, so you would say that diff x1, x2, 1 has dimension 2, as an example. Okay, now the whole point of looking at this is to try to prove a lower bound on the Waring rank of h of n comma d. But unfortunately, I don't even know a non-trivial lower bound on the dimension of the space. But I do know something, which is an upper bound on its dimension. Namely, the dimension of the space of partial derivatives of this polynomial is at most the golden ratio squared, the golden ratio to the power 2d. Okay, and the golden ratio comes up very simply here. Let me just explain. I'm not going to prove the lemma, but I'll just explain where this number comes from. So it turns out that diff of h n comma d is spanned by some set of determinants of matrices whose entries are polynomials. And there's some like explicit matrices like this, and their determinants span the space. They can be shown. And what matters is that there's a correspondence between these polynomials and subsets of the set 2d, 1 through 2d minus k of size k for any number k between 0 and d. Okay, but the number of such subsets of 2d minus k of size k is just 2d minus k choose k. So the total number of sets of any size k is this sum of binomial coefficients, which turns out to be the 2d Fibonacci number, or maybe the 2d like plus 1 Fibonacci number. And by the classic bound on Fibonacci numbers, it's at most the 2d power of the golden ratio. Okay. So I was trying to prove a lower bound on this thing, but so I was trying to prove a lower bound on the Waring rank of h n comma d, but I was unable to. But what Cornelius and I were able to do is, observe an upper bound on its Waring rank, observe an upper bound on the method for proving a lower bound. And so, I mean, it's not clear what this might be useful for, but you could ask if it's algorithmically useful. And yeah, I actually know a better upper bound on the space of partial derivatives, but I'll skip that right now. Recall the whole goal of everything here is to compute this inner product between some polynomial, here it's h of n comma d, and some unknown polynomial g that's given to us, right? And this quantity is going to be greater than 0 exactly when g contains a square-free monomial. So here's an idea. I'll just sketch it very quickly before ending. We'd like to compute this inner product between this particular polynomial h of n comma d, whose space of partial derivatives we know something about. We'd like to compute this inner product inductively using a circuit that computes g. And so what we'll try to do is the following. So given the circuit C, it computes a polynomial g, we're going to construct some new circuit C prime. And C prime it's just like a copy of C. So it has the same underlying graph. But what we'll want to do is, if this original circuit C computed a polynomial P at some gate, then what we want to compute at the corresponding gate in C prime is the result of differentiating this polynomial H by P. Okay? And if we succeed in doing this, then by the time we get to the output of C prime, we will have computed this inner product by its definition. So here's a little example. When we have a circuit C computing polynomial g, which is x1, x2 all times x2 plus x3. And what we want as the circuit C prime, so at this first input gate, what we want to compute is the result of differentiating h by the polynomial computed here, which is x1. So we want to compute the result of differentiating h by x1 at this first gate. Similarly, we want to differentiate h by x2 at this gate and h by x3 at this gate. And at this multiplication gate here, where previously we had computed x1, x2, we now want to compute the result of differentiating h by x1 and then differentiating it by x2. Okay, and so on until we want to compute this final output gate, which will contain the inner product that we want. Okay, so here h is h of 3 comma 3, which is just 4 times x1 and times x2 times x3. And let's just see how you might go about computing this from the input down. So first we want to differentiate h by x1. Okay, well, let's just do it. You got 4x2, x3. And similarly for the other gates, you could just differentiate them. Okay, that's what you got. And now, okay, so we have this multiplication gate here. We want to determine, what the polynomial computed at this gate is. And here we use the fact that if you apply a product of two differential operators, t1 times t2 times to a polynomial h, then what you get is just what you get if you first applied t2 to h, and then you apply t1 to that, which is the same as what you get if you first applied t1 to h, and then you applied t2 to all of that. So the idea is that you'll already have computed as one of your inputs t2 h, and then you just apply t1 to that. So that's just the rough idea. I'm running out of time, so I'll try to wrap this up quickly. So in this example, you see I'm writing things down in blue as monomials. There's a problem with this, which is that there are n plus d choose d monomials of degree n plus d in n variables. But we're only storing things in the space of partial derivatives. And we know that the space of partial derivatives has a very small dimension compared to the total space of monomials. Okay, so there's like a lot of redundant information. And the basic observation is that you shouldn't express polynomials as sums of monomials. You should express them using the smaller spanning set that we know for the space of partial derivatives. And then the key challenge becomes, what do you do at multiplication gates? Yeah, so the challenge is then, how do you perform arithmetic in the space of partial derivatives with respect to the spanning set? Okay, but using this, we show that if you have a skew arithmetic circuit computing polynomial g with non-negative coefficients, then you can decide if g contains a square-free monomial in deterministic time, the golden ratio to the power 2d times the size of the circuit times poly n. And this has applications to problems like detecting subgraphs of bounded path width, detecting outbranchings in graphs and colorful perfect matchings, and some matroid problems as well. Okay, so the concluding questions. First, can you improve the upper bounds on these quantities a epsilon of n comma d and a plus of n comma d? Because maybe it's an approach to obtaining much faster algorithms. It is an approach. Another question is, so we saw this polynomial h that had a smallish space of partial derivatives, and it was sort of similar to this elementary symmetric polynomial. Is it like the best, or can you find another polynomial f that also has this property that is close to the elementary symmetric polynomial in a sense, but its space of partial derivatives is even smaller? And this number, the golden ratio to the power 2d, appears in several papers in parameterized algorithms in the context of this problem, for example, detecting cycles of a given length. are there connections? Surely there are connections between these methods, but I have not been able to figure out what they are. It's kind of funny this number appears in both cases in these different papers. Final question, almost final question is, so we were computing linear combinations of these square free monomials, but what if you computed like higher degree polynomials in them, like the sum of their squares? For all I know, it could be much easier to compute the sum of the squares of the coefficients than it is to compute the sum of the coefficients. And finally, all of our methods are useful for unweighted graph problems. For example, question is, could you apply these to problems where the graphs have weights? So I haven't thought about that, but it's an interesting direction. Okay, so yeah, that's it. Thanks for having me. And okay.
Yeah, thank you very much, Kevin. So are there any questions?
I have a question.
Yep.
It's a very nice talk, Kevin, and it was very interesting to see how you can encode the graph structures using polynomials. So I was wondering, like, what other graph structures you can represent using like these kind of schemes?
Oh, so I didn't mention this, but you can do much more general things by methods. I think Fedor had a paper. So you can encode, for instance, this sort of generating polynomial for any graph, for any subgraph of bounded tree width. You can come up with some generating polynomial that's easy to evaluate. So that's for any subgraph of bounded tree width. And
so yeah. So I was wondering about like another particular question, like so instead of counting the number of cycles, if you want to count the number of paths, for example, number of simple paths in the graph, you can do in similar way.
Yeah, this same method applies, and yeah, the same method applies with some different generating polynomial, and much more generally for any subgraph of bounded tree width, you could do this.
Yeah, thanks a lot.
Yep.
And so what is your explanation with this magic golden ratio things? Is there some magic happening there, or is it just coincidence, or what is your intuition?
Oh, I don't know. I've looked at the papers, at your papers, and I'm not sure, like, because I thought that in your paper it appeared as like you were the minimum of some function. But in my paper, it appears as it's just some sum of binomial coefficients you get. So it's a little weird.
Yeah, weird. Yeah.
But there must be a connection, I think.
Okay, thanks a lot for a very nice talk. So any other questions? Okay. I think people are still, most of the people are on vacations. Like
okay.
Okay, thanks a lot, Kevin. And so usually we put videos online. Is it okay? So if you...
Yeah.
Okay, yeah, then thanks a lot. And
okay, yeah,
bye.
Thanks a lot for having me.
Yeah, bye.
Bye.